Before we move on to something completely new, I want to go back to one of the assignments that we've had. And that was very similar to what we've just been discussing. In fact, in that assignment, you were asked to define a lookups function, right, that takes a list of keys and then a table and produces a maybe of value of a list of values. And that was defined using sort of the classic list of pairs key value table representation. But it is exactly what we have just been doing, what we have just been defining. That is exactly corresponding to the mapM example that I have just been giving in the previous video. So if we replace this function here with a map of keys and values, so map AB, right? And we have our keys, our list of keys, then we have a very simple definition of this one now available. Let's have a look. We can just call mapM, right, of a function on our keys. And what is the function that we want to call on our keys? And we get a table here explicitly, right? So it's not necessarily the one that the example table that we have been using all the time. So I'm going to give a different name here, TBL, for our map, or we can also just call it M for map or something like that. And the function that we're calling here is indeed one that takes a single key, right, and then performs a lookup of that key in the table. Let's have a look. So this, and now of course, if we do this with our sort of professional finite maps, the EQ constraint from before is not enough. We do actually need an ORD constraint, right? But we could equally well have written this for the prelude version of lookup. It wouldn't be very much different. Let me just give a different name to this by using the prelude version of lookup, and then we can get away with the EQ constraint. So that is a very succinct definition of this lookups function that I had asked you before to write as part of the assignment, and we can write it much more simply now. But let's actually go back and take a look at mapM itself, how we define mapM itself and how we define sequence in particular. So mapM, right, when we defined mapM before, we defined it specifically for essentially for the IO type, but now we are in a situation where we know that we can generalize over the monad class. And the idea of mapM was just that we do sequence followed by map, right? So, or basically, or rather, we first do a map. But if we, sorry, I need to pick up the function here. Otherwise, it's not actually correct. And also, I'm getting conflicts now because of ambiguity. So let me actually briefly go and actually, this is a little bit surprising. Ambiguous. Yeah, okay, so we have to hide this from the prelude. So this is the definition that we had before, and if we go further and we also hide sequence, and we look at how we defined sequence before. So we said if we have a list of M of A's, we can turn that into an M of a list of A. We defined that one using pattern matching, or we could define it as a fold R, possibly. But let's do it using pattern matching. We said in the empty list case, we return an empty list, and in the xcons access case, we can just use the do block here, because as we now know, do notation works for anything that is an instance of a monad class. And we said that we first do x, and then we get a result out, and then we do access, and we get a result out, a sequence of access, recursive call. And then we have a single element A of type A, and we have a list AS of type list of A, and we can put these two things together using acons AS. That was one way to define sequence, but we also had another operator, again in the context of I/O primarily, that was called lift A2. And lift A2 was exactly capturing this pattern that we have here, that we have two things that we do in sequence, but the second one does not depend on the result of the first immediately. So the A is not being used in the second operation here. We are just combining the two results of the two things that we're putting in sequence in the end. That is exactly what lift A2 is doing. So we had a definition for sequence that is using lift A2 with a cons operator of x and sequence of xs. And in fact, this one we have to import from a different module, which is called control applicative. But we'll see that this definition in the generalized form also goes through. It also works in this particular case. We can use lift A2 in the context of I/O, but also in the context of maybe. And that is because, I have to reload here, well, lift A2 has an applicative constraint, but we have already seen that the monad class has applicative as a superclass, so even though we haven't seen exactly what the applicative class amounts to yet, we already know, because applicative is a superclass, that anything that is an instance of monad must in particular also be an instance of applicative. And so we can use lift A2 here. And indeed, we have already seen that we can define lift A2 in terms of bind and return if we choose to do so. All right. So we have lift A2 available on maybes as well. That is an interesting observation. So what does lift A2 do if we use it in the context of two maybes? Well, it's actually an operator that we've also already seen in the context of the assignments as, I think it was called lift maybe. It takes two maybe computations, and then we can choose how to combine the two results. If they're both successful, then we get a successful computation back that applies this operator to the two results. Right? In this case, we add them. In this case, we multiply them. In this case, we pair them up. And we could also, of course, put something slightly more complicated here that actually requires a lambda abstraction to properly define rather than a pre-existing operator. But in principle, that is the idea, right? And if any of the two constituent operations is actually nothing, then the whole thing yields nothing again. So the point remains that we have a whole lot of operations that we have at our disposal all of a sudden, just because we discovered that maybe supports this notion of sequencing and this notion of embedding. And that's rather fantastic, right? There is a large amount of functionality that we suddenly gain, and that goes beyond just being able to abbreviate and more nicely write this one function that we wanted to write. But in particular, we can also do that, right? And we can write things that are based on the notion of sequencing without having to spell that out, what it means in every step of the way. Okay, let's leave it at this for now with the discussion of maybe, and go to yet again a completely different example in the next video. Because just as maybe is a completely different type as I/O, and yet we have now discovered that they both support a common interface, that of a monad, these are not the only two examples. There are other examples as well. And we'll discuss another example, a completely different example, next.